All right, I'm just going to go straight to the point. This is a short talk, so I'm not going to take too much time. What I'm going to talk about today is some contributions we made to the open source testing community recently. And basically, it's a complicated name, but I'll break it down in the next slides. By the way, I'm a researcher. I work for Hitachi India. I got my PhD here in the United States in Colorado State University, and then I'm also a part-time metalhead. All right, so I'm going to break down the content into a little bit of backstory, the why we did this and why it's going to be important for you if you're in the testing community, or if you're building embedded products, that is. And then I'm going to talk a little bit about the actual contributions. So a little bit of backstory. This is a really interesting part of it. So here's the deal. If you are borrowing binaries, pre-compiled binaries, and we would want to test them, if you're in the security testing industry where you want to rip binaries out of embedded devices and test them, or just an embedded builder, right? You have binaries that you want to test. The traditional way to do that is take the binary out of the device, or before you put it in the device, emulate it within what's called a QEMU emulator. There are other emulators too, but QEMU is a really popular one. And then QEMU provides you facilities to emulate your peripherals, facilities to emulate the processor instructions by themselves. And once you've done the emulation, you actually test them. How do you test them? You send inputs and look at the code coverage, and you're happy, right? Well, you get bugs. Sometimes you use the code coverage to create more inputs. This is all great, except there's one problem. The problem is this. When you test, your code doesn't always progress the way you like it to. It's not that I started testing and all of my code got tested in 1 hour and I'm happy I go home. It doesn't happen that way. You get stuck in what's called roadblocks. And these red arrows that I have on top are what we refer to as roadblocks, meaning that there were some conditions on those branches that your fuzz tester, let's say AFL++, for example, could not meet. Right? And this is a very common problem. You go to Google's fuzz bench, and you would see commonly that the amount of code coverage is really, really low. And how do you fix this problem? Well, the way to fix this problem is you can just go and manually set those roadblock branches to true. It will hamper the testing to some extent, but people really do that. So if people do that, what's the problem here? Well, the problem is QEMU by itself won't let you do that. AFL++ could still craft the inputs for you, but QEMU would not let you do that. Well, what are the alternative strategies then? One way is QEMU provides you some sort of plugins. You can write small plugins and try to play with the memory. You can, but unfortunately it's one way right now. The developers don't really encourage doing the other way around. That is, you can't really fiddle with the runtime environment. The other option is use the native GDB. Great option. There are papers and technical works, academic works that have really done that. You could do that. Problem is, you can see the GDB talks over sockets. TCP, life slower. Your texting is going to become really, really slower. The other option on the right-hand side is what they refer to as the Pythonic overlays, unicorn and killing. What they do is they will let you write your own Python programs, and your fuzzer will interact over the Python environment to your internal binary. All that is great, but it's Python. So, interpreted languages, you have overheads, things become slow again. But the bigger problem also is that the fuzzer itself, AFL++ in this case, does not really have a really good support for such Pythonic systems. In fact, you have to write your own bug catching for every single program that you're testing. Not really good, right? Because you want to reuse as much of the fuzzer system as you can. So that's where we come in. We have already made the contribution to the AFL++ tool. So if you're using AFL for your testing, gray box testing, then you would probably go and find that in that location that I have on picture. Now, just a slight touch of the inner workings. But there were two major things that we had to deal with. One is we didn't want to make much of a change to the QEMU code. That's obvious reasons. Much change means if something happens, then code might break. We don't want to do that. The other point was, which I'll come to a little bit later. Now, if you see there are two components in there, we actually put much of the bulk of the load on the orange side of things, which is the TCG plugin. And on the right-hand side, you have the GDB stuff, which is provided by QEMU, where we make approximately 6 lines of change. That's it. That way, we take out most of the load on a plugin and put it less on QEMU. Now, IEA is same. You write your hook functions on the left-hand side. We install them as breakpoints, done. When the breakpoints hit, we call the hook functions. Simple idea. But the problem is, we install a small trampoline in the middle, just so we didn't have to do the actual breakpoint calling or the hook function calling within QEMU. We moved it to the plugin. Saves you time and space. And then in the runtime routing, it was all straightforward, right? So you get the breakpoint, you call the hook, whether you want to keep the hook or not. We do allow users to mention whether you want to keep the hook or not. That means whether you want to still keep breaking on that point and making changes or not. Anyways, whether you want to do it or not, we could remove the breakpoint accordingly and continue. The white logical blocks symbolize that, but there was one problem that we faced. Say you put a hook on instruction A, and you come back, say you want to say that, oh, I want to continue from instruction A. Now what happens? When your hook is done, you hit instruction A again, and the hook again gets called. It goes into recursion. When we faced that problem, we said, what do we do with that? Well, so to do that, we said, okay, if you return to the same address, we just enable single stepping. If you're in the debugging world, you would be aware of single stepping. We enable single stepping, remove the breakpoint. Later on, when the next time single stepping hits back, then we reinstall the breakpoint and remove the single step. That way, we fix that small problem of recursive hook calls. And then on top, one last thing is, we recommend, or we actually mandate naming hooks as hook underscore the address where you want to make your changes in the program. That helps us to call the hooks really, really fast using real-time dynamic loading that Linux, for example, provides, such as dlopen and dlsim, right? So that's the main bottom line. I'm going to go quickly through 2 demos. Just going to show you how we use it. Here's one small program that I have on the right-hand side. And in the small program, I have a mem copy in there, which obviously is one of the most notorious statements all over in underlying computing. It's a stack smashing buffer overflow. You can see that there's a C data buffer, which is 7 bytes, and you can actually overflow that with any number you want. Now, I want to find that bug. It's a straightforward program. It should be found. Let's try it without our solution for once. Let's see what happens. Straightforward AFL without our solution, and it says that it results in a timeout. Well, that's because I'm actually trying to read from a CAN bus. CAN is a very popular industrial protocol. If you're in the ICS world, you're familiar with CAN, or in the automotive world, you're super familiar with CAN, right? So it's trying to read from the CAN bus, but it cannot find a CAN bus on my system, so it just results in a timeout. What if I wrote a small hook to emulate the CAN peripheral? So what I do in bottom here is I write a small hook, which is towards the left, I say is hook. And in that hook, I read from the standard input. That's where AFL or fuzzers put their inputs. You read from the standard input, and you just pass it back to the CAN frame. That's it. You've emulated the CAN bus without the actual CAN bus, right? Now, let's see what happens if I do, well, the results are already on screen, but if I did that, with that little hook in there, with our hook and bridge, you roll. So, and it's just the testing going on, and it already found the bug. So, bottom line, without the hook, you would get these side of issues, not being able to test, getting stuck in the parts of the program. But with the hook and bridge, which were provided for AFL++, you can now redirect inputs from the standard input to what is supposed to read from some sort of a sensor or CAN bus, something you don't have available if you're in the ICS testing world. So speed-wise, I just mentioned that the other ones have a little bit lower speed, but speed-wise, as you can see, we have almost a 10 times boost on a pretty relevant Intel server that we were using. And that's almost the end of my talk. It was a rapid talk, but If you want to contribute, please do. I'm not going to claim that it's all of it. You can always add to it. We don't have a lot of operating system support right now. Just Linux only, as I mentioned, DL Open, DL Sim. You can, the one feature that I would really love to have next is the facility to debug some of these hooks. Right now, you can write your hooks and kind of print from the hooks. QEMU lets you do that. But then I would want more debugging features into it. So one way would be if you can concurrently run these hooks, which leverage the GDB of QEMU, and still be able to use the actual GDB. That is one problem. The other one that I would really love to do is actually modify the hooks in real time. That would let you experiment with the hooks that you create, right? Kind of debug them and experiment with the hooks in real time. You could put much more as you want to. Just pull a PR from AFL++. They're awesome people. And yeah, that would be the end of my talk. And yeah, I'm Subhojeet Mukherjee from Hitachi, and I could take some questions now if we have time. No, thank you. Questions? I know it was a rapid talk. It was 10 minutes, or maybe even faster than that. I made it, but no questions? Okay, I'm here for the next 2 days. We could talk a lot about low-level testing stuff. That's what I do. I did my PhD in that area, so yeah, we can talk. Thank you. Thank you so much.